Welcome to Onondaga High School. I'm Brian Brown, and today in this chemistry video we'll be looking at our last set of notes, day 7 of electron configurations. And what we'll be concentrating on here are how we can use the periodic table to do the same stuff we did with the off-bout chart, but easier, and also how to do our next two electron configurations, the noble gas configuration, sometimes known as shorthand notation, and then the electron dot, which is not in your chapter, but makes the natural conclusion of our ideas here. So first off, I use a very specific periodic table. So you'll notice this one may look different from maybe the one you're looking at. So I always make sure I use this one with my students because it shows very specific information about the D and F sublevel. And it makes it a lot easier because honestly, by off-bow, they fill in a very certain way. Now, there are exceptions, but filling it this way, there are less exceptions. And this, to me, is a much less confusing periodic table. So you should really go to the resource page and print this out if you don't have it. Now, what we're going to do with our periodic tables, we're going to block it off so that you can see how the periodic table actually gives you the same information as the off-bow chart, but it's quicker, easier, and more useful in a lot of other situations. Now, because of what we're going to do to this, I won't let you use your periodic table in the test, but I will give you a non-laminated periodic table for this test, and one of the first things you should do is block it off if you so wish. You don't need to, but that's why you get a non-laminated periodic table for this test. Now, you'll notice we have 4 general regions on the periodic table here, and that's because it, not coincidentally, matches up to our 4 different shape sublevels, S's, P's, D's, and F, and that is not a coincidence. So, first one we're going to look at is the one on the far left here. So I want you to make a nice rectangular box. And yes, I know there's a notch out, but draw it this way because we're going to stick something there in a second. And what we really have here are not elements, but electron positions. So this is the first electron. And technically, this would be the first electron in any atom. And the third, and the fourth, and the 11th, and the 12th. So what are we missing here? Well, this would be the second. So what we're actually going to do here is we're going to take and we're going to move helium over there. So I want you to put a 2 with an HE in that box. Now, this is 2 across, and that seems to correspond with how many electrons it would take to fill an S sublevel. So we're going to label this S. And the first time we see an S is the first energy level, and every energy level beyond. So we're going to number this down the left side, 1, 2, 3, 4, 5, 6, 7. Now, remember that little chunk up there, I said we're going to take helium, so we're going to get rid of that where it's at, and we're going to stick it over there. So that's electron position 2, which would be where helium is in terms of our electrons. So it better fits over there when we're doing electron configurations. I know it's noble gas, and we'll get into why later, but that's where it fits by our blocks here. Now, that would be our S block. Now, next on the far right, we've got a block over here that I want you to, and if you're color coding this, make this the same color. There's a reason for that later, you'll see. Now you'll notice that this is 6 across, and once again this represents electron positions. So 31st, 31st, 32nd, 33rd, 34th, those are electron positions. And that's where they would end up being in any atom. Now what actually is this? Well, it's 6 across. That would imply 3 orbitals. What sublevel has 3 orbitals? Well, that would be the p sublevel. And then what energy level is the first time we see a p? Well, it's the second. So we're going to start numbering this 2, 3, 4, 5, 6. And remember, 2 is at the neon, not at the helium there. Now, if you have things down in this region, that's fine. Just extend your box down and call that a 7. Not a big deal because we'll never be talking about any of those. But yes, you could extend that down and call that 7 if you so wished. Now, next part of the periodic table is smack dab in the middle. You'll notice 21 to 30, that's 10 across. 10 divided by 2, that would be 5 orbitals. So what is 5 orbitals? Well, that would be our D sublevel. Now notice I'm putting this in a different color. And if you're going to color code it, I recommend you put it in a different color. Eventually you'll see why. And we're going to label this the D block. Now what's the first energy level we see at D? Well, 1 was S, 2 is P, so D would be 3. Follows a nice structured pattern here. So we're going to label this 3, 4, 5, and 6. I know you kind of have to squeeze them in there, but you can get them to fit. And that would be our D sublevel. And once again, these represent electron positions. So the 9th electron in any atom would be going right here in the 5th level D, and it would be 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons in. So the 9th electron into our 5th D sublevel would be where the 79th electron goes. Now, the only thing left is that thing we pulled out. We talked about this earlier in the year. 57 through 70 seems like it needs to go right here before LU and after BA. Well, and rather than pushing the periodic table all the way to the right, we're going to separate out these 14 electrons. And rather than stack them like a deck of cards, we're going to spread them out across the bottom. So notice there are 14 across. 14 divided by 2, that's 7. What shape of orbital has 7? Well, that would be the F. And when's the first energy level we see in F? 1s, 2p, 3d. Oh, must be 4 for F. So we number it 4 and 5. And remember, it fits right here between these two and right here between those two. So before we get to the 5D, you'll notice by electron number, because that's what these are, is electron positions. After 56, where BA is, we then, for 57, come down here. So after 6s, this shows next we hit 4f. And that's exactly how it happens with the vast majority of atoms. Now, I'm going to mention this once, and I'm only going to say it once, but you will see some periodic tables and have some chemistry teachers that talk about after barium, the 6s, you then get to La, and we're going to call that 5D1 because it seems like it fits in. Honestly, that makes it more confusing. While there are, I think, 4 out of these 14 that do odd things with electrons, 10 of them follow as if after 6s you hit 4f. We're not going to be looking at these electron configurations in first-year chemistry or in second-year chemistry with a fine-tooth comb. So it doesn't really matter. It makes more sense to look at how most elements exist, and most of them behave as if after the 6s comes the 4f. Now, after the 7s would then come the 5f. And yes, in the 5f block, there are a few more that don't behave that way, but the majority of them still do behave as if you go 7s and then 5s and then 6d. So it makes sense to me not to talk about how the first one's in or D1 and then it's just added extra useless information that you don't really need to know for first and second year chemistry. Yes, if you're going to become a chem major and you're in your third year of science, you're probably going to get into understanding these maybe at a deeper level, but not for us. So after the 7s comes the 5f. And remember, the atomic numbers are electron positions, and that reminds us of that. So here's how we block our periodic table. And this actually gives everything that the Aufbau chart does, plus a whole lot more. Now, if you recall yesterday, we finished up with looking at electron configuration. So let's say I want to do the electron configuration of lead. Lead is a mouthful. It's got a whole bunch of stuff here. Now, how does this periodic table on the previous page help me with that? Well, let's step back a second and see how we can get this. And I know it's going to take me a few seconds to write it, if I was going to write it out as I was saying it, but you'll see how easy it is to do this. So we're going to lead. So we want to describe all the electrons in lead. So electron 1 and 2 are right here. So the first electrons in lead will be 1s, and it will take 2. Electron 3 and 4 are here. So then comes 2s, 2. Now 5 through 10 are here. So then comes 2p6. 11 and 12 are here. So next comes 3s2. 13 through 18 are here. So next comes 3p6. 19 and 20 are here. So next comes 4s2. And then we hit our 21 through 30. That's 3d. And that would be 10. And then 4p6. And then 5s2. And then 4d10. And then 5p6. Starting to run out of room here, so I'm going to wrap it around. And then next comes 55 and 56. That would be 6s2. Oops. Let me erase that, so I avoid any confusion there. So this is our 6s2. And now notice number 57 would come next. That's down here. So those come next. So then we have 4f, and it's 14 across. And then 71 is back up here, and that's 5d, and it's 10 across. And then we finish 81 and 82. They're in the 6p, and it would take 2 of them to get there. And that's how the periodic table makes this so much faster. I know that was a huge one, 82 electrons, but still it's so much faster to get this information with the periodic table than it is with the Aufbau chart. So much quicker, so much easier to use it. Remember, they're electron positions, and you slide your finger through and follow the numbers. That's all you got to do. Now, That's a mouthful, and that includes a lot of information about electrons we typically don't care about. Because the most important electrons, the one that interact with the outside world, are the ones that are on the highest energy level, which has got a fancy name. It's called the valence level. So it'd be nice to skip a bunch of electrons there in the middle anyway. Well, the way it works, and this is where my colors come in the picture here. So let me wipe this clean. Oh, see if I can try and clean the slate here a little bit so it's less visually confusing. Okay, now you'll notice that the S and P are in red and the D and F are in blue. Now, the reason that they're in different colors is because they signify something very different. Notice as I'm filling, after 11 and 12 comes 13, 14, 15, 16, 17, 18. And then I go to then the third level. If I'm looking at these 18 electrons, the third energy level is my highest level. And it's got 2 in the S and it has 6 in the P. But once I go to electron number 19, now I'm in the fourth energy level. So the third is no longer my highest energy level. So when I get to electron 19, now my highest energy level is in the fourth energy level. But notice what kind of happens when I get from calcium, number 20, to the 21st electron. It's going into the third level D. It's not going to the outside, it's going to an inner energy level. So these electrons aren't going on the top level, they're going on the inside. But then when I get back to the P's, yes, now I'm going to the outside again. So when you really look at it, when you get to D's and F's, they're never on the outside. When we get to a D block or an F block, we're always adding electrons on the inner or core levels of the atom. So it would be really nice if we could try and skip a bunch of electron information to make this a little bit easier to do. Now, since S and P's are the only ones that are on the outside, and when I have a complete full set of S and P, so my fourth S and my fourth P is all filled, that would be 8. My third S and third P is all filled, that would be 8. Notice it's 8. It's always going to match up with our noble gases over here. So the last time I had a full valence level, which would be 8, because only S's and P's can be on the top, was my last noble gas. So if I go back to my last noble gas, I'd be guaranteed to be talking about electrons on the inside of the atom. Well, in lead, what's our last noble gas? Well, I need to know that to do my noble gas or shorthand notation. I usually call it noble gas configuration because it's more descriptive. Like electron configuration, except the inner level electrons are described by writing the last noble gas in brackets and then describing the other electrons that come after. So what does that look like over here? Well, let's say we're looking at lead. That's the one that the example was given in that we wrote out a second ago that took forever. Lead is right here. Now that is number 82. So I'm going to go backwards. 82, 81, 80, 79, 78, 77, 76, 75, 74, 73, 72, 71. Oh, and then I got to go through 70, 69, 68, go through all those, 57, 56, 55. And then finally, I'm back to a noble gas. So the last noble gas before lead was xenon. Now, instead of counting back, it's easier just to go up one and all the way over, and you're always going to be at your last noble gas. And you're guaranteed to be talking about inner level electrons when you go to your last noble gas. So what we're going to do in noble gas configuration is we're going to skip all of the electrons that are in lead, which would be that set right there, all the way up through, I'm sorry, all the electrons that are in xenon, because that was our last noble gas, which would end in 5p6. And we're just going to describe the electrons after. So those electrons are all described by saying Xe in brackets. And then after that comes 6s2, 4f14, 5d10, 6p2. So that's what I write out. So literally, I go back to my last noble gas, which would be xenon, and I describe those electrons by saying Xe in brackets. That means all the electrons inside xenon. And then I have to describe electrons 55 and 56. That would be 6s2. And then electrons 57 through 70, that would be 4f14. And then 71 through 80, that would be 5d10. And then I finish up with my 6p2. So I get to save a ton of time if I go back to my last noble gas. But yet I still have information about my highest energy level, which in this case would be the 6th energy level. These are highest energy level electrons, and these are highest energy electrons because 6 is bigger than 4 and 5. So I still have all my information about my highest energy level electrons, but I got rid of a whole bunch of core or inner level electron. Now, not all of it. I still have 4F14, 5D10, and those are on the 4th and 5th level, but I at least got rid of most of it. So that's really what we're doing in noble gas configuration. It's a way to simplify the process immensely by going back to the last noble gas and then describing all the electrons after. So write the noble gas configuration for radon. So remember, radon is way over here. So I go back to my last noble gas up and all the way over. That would be Xe. So I'm going to put Xe in brackets, and that means all the electrons in xenon. And then I go through and describe electrons 55 through 86. So that would be 6s2, then down to the 4f, and there's 14, then up to the 5d, and there's 10. And then finally in the 6p, I've got 1, 2, 3, 4, 5, 6 of them. So that would be my noble gas configuration for radon. So xenon, 6s2, 4f14, 5d10, 7p6. That would be noble gas configuration for radon. So I know radon is a noble gas, but if you just say radon in brackets, you haven't said anything. So go back to your last noble gas and describe the electrons after. Okay, that brings us to our final configuration. And this is the most abbreviated of them all, so it's the quickest and easiest to do once you really learn how to do it. And that's the electron dot notation. Remember, this is not in this chapter in the book, but it makes perfect sense to talk about it with what we're doing in this chapter. Now, we're going to write the element symbol for the element we're talking about, and that represents every inner level electron. It's not like last noble gas where sometimes we miss a few in the F's and D's. It means every electron on the inside of that atom. And then you put dots around it to show the valence or outside electrons. Now, when you go to draw them, space out your electrons. So picture a box with 4 sides, and space out your electrons around and never put more than 2 on a side. Now, when you really think about it, since the S's and P's are the only ones on the outside, there's really only going to be 8 dots we ever put. So I'd put like the first one there, the second one, the third one, the fourth one. Now, why am I spacing these out? Well, electrons are negative things. They're going to repel each other. They're going to spread out. But once I've got one on each side and I need to draw more, now I start doubling up. And once again, I don't really care where you double up. Just double up somewhere. So another one, another one, another one, another one, and now I've got all of them I can possibly ever have. So keep in mind, you can only have up to 8 valence electrons. That's your max. So if you start drawing 24 electrons, you've made a mistake and you missed the boat. So you can only have up to 8. So what would carbon look like? Well, remember, carbon was 1s2, 2s2, 2p2. Its highest valence level would be the second, because this is on an inner level, the first level, and the highest energy level is the second. Remember, the number in front of the S and P represents the energy level. So the S2 and the P2 here are both in the second energy level. And that's a total of 4 electrons. So carbon needs to have 4 dots around it. So literally, 1, 2, 3, 4 dots. Space them out, you're good. That's what the electron configuration for carbon means. Remember, the symbol itself means those 1s2 electrons. And if we have something farther down on the table, we get to skip a ton of electrons and only talk about what's on the highest level. Now, why is this so quick and easy? Well, think about it. All you really have to do is count across the S&P block, because in the first row of the S, those are all of our S1s. Those all have 1 dot. The second column in our S block, those would all be S2. Those all have 2 dots. And then we get the D's and F. We're going to skip and talk about that in a second, because remember, those are on the inside. And then that gets us to the boron, aluminum, and so forth on down. Well, that would be the P1 block. And those are in the same level as the S's we just talked about. So literally, boron would be an S2P1. Well, that's a total of 3. So literally, just count across 1, 2, 3, 4, 5, 6, 7, 8. And that's how it works. So it's quick and it's easy when you look at the periodic table. So we'll look at that in a second because I want you to see it visually. Now remember, the most any element can have an 8, so never draw more than 8 dots. And all the D's and F's, to get to a D or an F, you had to go to a higher level S and add 2. So while there are exceptions to Aufbau in the D and F block, who cares? You don't need to know them. So you can just assume they're all 2 and leave it at that. So let's jump back a second here and look at a periodic table. So I got to jump back a whole bunch. Now, what was I really saying? Well, that's tied to why I color-coded things. My S and my P's are the only ones that can be on the valence level, because to get to a D, I had to go through a higher level S and put 2. So those are going on the inside. So literally everything in the first column slate clean again here. Everything in this first column, those are all S1. These would all be S2. These would all be S2P1, that's 3, and then 4 and 5 and 6 and 7 and 8. And remember, we moved hydrogen over here. That would have 2 dots. So it's as easy as just counting across the S and P block. And why do the D's and F's all in general have 2? Well, to get to any D or F, you had to go through a higher level S and put 2. So scandium, 21, well, we had to go through 19 and 20. That's in the 4S. And look down at your F block. Remember, to get to the 4F, we had to go through the 6S and put in 2 to go from 55 to 56 to 57. So they're way on the inside. So the whole DF, consider it 2 and leave it at that. And that ends our chapter over the electron and electron configurations.